Hello, and thank you for joining me on this tranquil journey through the cosmos. Tonight, we will slowly drift into a state of calmness as we explore the vast expanse of our universe, its beginnings, its mysteries, and the boundless future that lies ahead. From the incredible burst of energy in the Big Bang to the formation of stars, galaxies, and the intricate forces that govern time and space, we will journey through the wonders of the cosmos. As we reflect on the birth of planets, the secrets of black holes, the search for distant worlds, and the endless possibilities that await, let your mind gently wander among the stars. If you enjoy these peaceful moments, please consider leaving a like, subscribing, or sharing your thoughts below. Your support helps others find their way to this serene space. For now, just breathe. Let your body relax, release any tension, and allow your mind to drift into the infinite. Let's begin. The most incomprehensible thing about the universe is that it is comprehensible. These words from Albert Einstein remind us of the incredible paradox at the heart of our existence. Despite the universe's vastness, complexity, and mystery, we are able to make sense of it. Through observation, discovery, and inquiry, we have come to understand its deepest secrets: how stars are born, how galaxies evolve, and even the forces that shape time and space. In this journey, the incomprehensible becomes comprehensible, and with each new insight, the universe reveals itself a little more. The Big Bang, often described as the birth of everything, marked a moment where space and time themselves began. Around 13.8 billion years ago, the universe suddenly expanded from an infinitely small, hot, and dense point. This event wasn't an explosion in space, but an expansion of space itself. During the first few moments, the universe was a soup of fundamental particles and energy. As it cooled, these particles began to form the basic building blocks of matter, setting the stage for galaxies, stars, and everything that would follow. Our very existence traces its origin to that explosive event. In the aftermath of the Big Bang, the universe was filled with radiation, a remnant of the intense heat from its birth. As the universe expanded and cooled, this radiation began to stretch, shifting it into longer wavelengths. What we observe today as the cosmic microwave background, CMB, is this ancient light, now cooled to just a few degrees above absolute zero. It provides a snapshot of the early universe, offering crucial clues about its age, composition, and how it evolved. The CMB is like a fossil, revealing the conditions under which the universe began to form. As the universe continued to expand, the first atoms began to form, roughly 380,000 years after the Big Bang. Initially, the universe was so hot and dense that atoms couldn't exist. Photons would scatter off free electrons. However, as the temperature dropped, protons and electrons combined to form hydrogen atoms. This allowed light to travel freely for the first time, creating the cosmic glow that we now detect as the CMB. These atoms form the building blocks of everything we see in the universe today, from stars to planets to life itself. In the depths of space, the quiet whispers of an ancient force continue to shape everything we see. It is a force invisible to the naked eye, yet it binds everything together: gravity. After the Big Bang, as the universe expanded and cooled, gravity began to pull matter together, forming the first atoms and eventually creating the building blocks of galaxies. Without gravity, the universe as we know it would never have emerged. From the formation of stars to the way galaxies dance around one another, gravity is the silent architect behind the grand design of the cosmos. The first stars, known as Population 3 stars, formed a few 100 million years after the Big Bang. These stars were different from those we see today. They were massive and composed almost entirely of hydrogen and helium, the only elements present in large quantities at the time. Their birth marked a key turning point in the universe's history, as the energy and light they produced began to illuminate the universe, ending the cosmic dark ages. These early stars paved the way for the complex structures that would follow, including galaxies, black holes, and heavier elements essential for life. One of the most fascinating discoveries in modern astrophysics is the existence of dark matter. While we can't see it directly, its gravitational effects on galaxies and galaxy clusters are undeniable. Dark matter makes up about 27% of the universe, compared to the 5% that we can observe as ordinary matter. It doesn't emit or interact with electromagnetic radiation like normal matter, which is why it remains so elusive. However, its presence is inferred from the way galaxies spin and the way light bends around massive objects, a phenomenon known as gravitational lensing. In addition to dark matter, scientists discovered another mysterious force called dark energy. Dark energy is thought to make up about 68% of the universe and is responsible for the accelerated expansion of space. Unlike gravity, which pulls matter together, dark energy pushes galaxies apart. This discovery has reshaped our understanding of the cosmos, suggesting that most of the universe is made of invisible forces. Dark energy remains one of the greatest puzzles in cosmology, challenging scientists to rethink the fundamental nature of the universe itself. The life cycle of a star begins when clouds of gas and dust collapse under their own gravity, eventually igniting nuclear fusion in their cores. This fusion process generates the energy that powers stars, creating light and heat. Over time, stars burn through their fuel, and their fate depends largely on their mass. Smaller stars like our Sun end their lives gently, shedding their outer layers and leaving behind a dense core, a white dwarf. Larger stars, however, explode in spectacular supernovae, dispersing heavy elements into space and seeding future generations of stars, planets, and life. Stars are born, live, and die in cycles that contribute to the richness of the universe. When a massive star reaches the end of its life, it undergoes a supernova explosion. This is one of the most violent events in the universe, as the star's core collapses under gravity, creating an enormous burst of energy. These explosions are so powerful that they can briefly outshine an entire galaxy. The remnants of these supernovae often collapse into black holes, regions of space where gravity is so intense that not even light can escape. This marks one of the most mysterious aspects of astrophysics. Black holes are among the most fascinating and enigmatic objects in the universe. Their intense gravity warps space-time, creating a point of no return known as the event horizon. Once something crosses this boundary, it is inexorably drawn toward the singularity at the center, where space and time cease to function in the ways we understand. Despite being invisible, black holes can be detected by the way they influence nearby matter, such as when they pull gas from a companion star or warp light from distant objects. Scientists are still grappling with the strange and complex nature of black holes. Time dilation, a concept rooted in Einstein's theory of relativity, describes the way time slows down for an object moving at high speeds or near a massive gravitational source. The faster an object moves, or the closer it is to a black hole, the more time appears to slow down for it relative to an observer farther away. This effect has been confirmed through experiments involving high-speed particles and satellites orbiting Earth. Time dilation also has practical applications, such as the need to adjust clocks on GPS satellites to account for the difference between time on Earth and in orbit. The Hubble Deep Field is an extraordinary photograph taken by the Hubble Space Telescope, capturing a tiny, seemingly empty patch of sky. Despite its small size, the image revealed thousands of galaxies, each containing billions of stars. This photograph is one of the most significant achievements in modern astronomy, allowing scientists to look back in time over 13 billion years to witness the formation of some of the earliest galaxies. The Hubble Deep Field shows how vast and ancient the universe is, and reminds us that there are countless cosmic wonders yet to be discovered. The expansion of the universe is one of the most remarkable features of our cosmos. Observations of distant galaxies show that they are moving away from us, with the furthest ones traveling at speeds faster than light due to the expansion of space itself. This discovery led to the realization that the universe has been expanding since the Big Bang and will likely continue expanding indefinitely. As galaxies move further apart, the universe will become colder and more diffuse, but the exact fate of this expansion, whether it will slow, speed up, or reverse, is still uncertain and remains a topic of intense research. At the heart of the universe's expansion is a force known as gravity, which governs the motion of celestial objects. Gravity causes planets to orbit stars, stars to orbit in galaxies, and galaxies to cluster together. It shapes the structure of the cosmos on both the largest and smallest scales. Yet, despite its importance, gravity remains one of the most mysterious forces. It is the weakest of the fundamental forces, yet it dominates over vast distances. Scientists are still trying to reconcile gravity with the other forces of nature, such as electromagnetism, in a theory of everything. While the universe is vast and seemingly endless, the possibility of life elsewhere is a subject of great intrigue. We know that the basic ingredients for life, carbon, water, and organic molecules are common throughout the cosmos. However, the exact conditions required for life to flourish remain a mystery. Scientists have long speculated about the possibility of microbial life on Mars or beneath the icy crust of Europa, one of Jupiter's moons. With the discovery of exoplanets, planets orbiting stars outside our solar system, our understanding of where life might exist is expanding, opening up new frontiers for exploration. The search for exoplanets has become one of the most exciting frontiers in modern astronomy. Thousands of exoplanets have been discovered, many of which lie within the habitable zone of their stars, where conditions might be right for liquid water to exist. Some of these planets are similar in size and temperature to Earth, raising hopes that life could exist elsewhere in the universe. Scientists are using increasingly sophisticated instruments to study these distant worlds, looking for signs of atmospheres, water, or even biological activity that might suggest the presence of life. The fate of the universe is a topic that has puzzled scientists for centuries. Will the universe continue expanding forever? Or will gravity eventually slow its growth and cause it to collapse in a big crunch? Other theories suggest that the universe could continue to expand at an accelerating rate due to dark energy, eventually reaching a state known as the Big Rip, where galaxies, stars, and even atoms are torn apart. These theories offer glimpses into the distant future, but the true outcome of the universe's fate remains a profound mystery that we are still striving to understand. What if the universe's beginning wasn't a simple explosion, but a cataclysmic, mind-bending rupture in time and space? The Big Bang not only created all of matter, but also space itself. In the first moments of existence, the universe expanded incredibly fast, a process known as cosmic inflation. During this brief period, the universe grew from smaller than an atom to larger than a galaxy in an instant. This rapid expansion smoothed out the universe, allowing galaxies and stars to form. Yet, the true nature of inflation is still a mystery. Was it a temporary event, or the key to understanding everything? In the vast emptiness of space, there are regions where the very fabric of the universe becomes a battleground between light and gravity. Black holes, with their immense gravitational pull, bend light around them, creating an effect known as gravitational lensing. This strange phenomenon allows us to observe objects that would otherwise be hidden behind a massive object. When light from distant stars passes near a black hole, it curves and magnifies, revealing glimpses of far-off galaxies and the mysterious depths of space. Gravitational lensing has become a powerful tool for scientists, providing a way to study the hidden corners of the cosmos. There is a place where time itself is forever stretched, where the ordinary rules of the universe bend and twist in ways we cannot fully comprehend. At the edge of a black hole, called the event horizon, time slows to a crawl. To an observer far away, an object falling into the black hole would appear to freeze at the edge, as if trapped in an eternal moment. This bizarre effect, predicted by Einstein's theory of relativity, challenges our very understanding of time and space. Yet, what truly happens beyond the event horizon remains a tantalizing mystery. The first stars to burn in the universe were not like the ones we see today. They were enormous, blazing balls of hydrogen and helium, devoid of the heavier elements that would later form planets and life. These stars, known as Population 3 stars, were the universe's first generation, born from the primal soup left by the Big Bang. When they died, they exploded in massive supernovae, scattering elements like carbon, oxygen, and iron into the surrounding space, seeding the universe with the building blocks necessary for future stars, planets, and even life. There is a force within the very heart of galaxies that keeps everything in motion, a force so powerful that it can swallow entire stars. Supermassive black holes, which reside at the centers of most galaxies, exert immense gravitational pull on their surroundings. These black holes can be millions or even billions of times more massive than the Sun. As matter spirals into them, it heats up and emits intense radiation, making these galactic cores some of the brightest objects in the universe. They are enigmatic, invisible forces at the very center of the cosmos, shaping galaxies with their gravity. Imagine standing at the edge of the universe, witnessing the cosmic horizon expand endlessly before you. The universe is not static, but constantly growing. Over billions of years, galaxies have been drifting further apart, propelled by the mysterious force of dark energy. This accelerated expansion has been occurring since the discovery of dark energy in the late 1990s, and it continues today. defying the gravitational pull that would otherwise slow down this expansion. The exact cause of dark energy remains unknown, but its effects are undeniable, reshaping the future of the cosmos and possibly leading to a universe that will grow colder and emptier with time. Far beyond our reach, in the far corners of the universe, there are galaxies so distant that their light takes billions of years to reach us. Observing these distant galaxies is like looking back in time, as we are seeing them as they were long ago. Some of these galaxies were born only a few 100 million years after the Big Bang, making them some of the first structures to form in the universe. Studying these ancient galaxies gives us a glimpse into the universe's early stages, revealing how it evolved from a hot, dense fog of particles to the intricate web of stars and galaxies we see today. Time itself is not a constant. It can bend, stretch, and distort, especially in the presence of intense gravity. This phenomenon, known as time dilation, is a direct consequence of Einstein's theory of general relativity. When objects move at extremely high speeds or are near massive gravitational sources like black holes, time behaves differently for them compared to objects far away from such influences. This effect has been experimentally confirmed, with atomic clocks on satellites running slightly faster than those on Earth due to the difference in gravity. Time dilation is a reminder that our experience of time is relative, shaped by the universe around us. What lies beyond the boundaries of the observable universe? We can only see a fraction of the cosmos, limited by the speed of light and the age of the universe. Beyond the observable limit, there may be countless galaxies and cosmic structures yet to be discovered. The universe could extend far beyond our current understanding, its true size and nature hidden from us. Some theories suggest that beyond our observable universe, there could be other universes, each with its own laws of physics. This idea, known as the multiverse, challenges our understanding of reality itself, hinting at an even grander, more complex cosmos. The search for life beyond Earth has never been more urgent, as scientists now turn their gaze toward distant worlds that could harbor conditions suitable for life. The discovery of exoplanets, planets orbiting stars outside our solar system, has been a revolutionary step in this search. Many of these planets are located in their star's habitable zone, where temperatures might allow liquid water to exist. The presence of water is considered one of the key ingredients for life as we know it, so these exoplanets offer the possibility, however distant, that life could exist elsewhere in the universe. What if the universe is a much stranger place than we could ever imagine? In quantum mechanics, particles can exist in multiple states at once, a phenomenon known as superposition. This bizarre behavior has been experimentally observed in the smallest particles, like electrons and photons. At the quantum level, particles can be entangled, meaning that the state of one particle can instantaneously affect the state of another, even if they are separated by vast distances. These strange effects defy our everyday understanding of reality, suggesting that the true nature of the universe might be far more mysterious and interconnected than we realize. At the center of nearly every galaxy, there lies a supermassive black hole, an object so dense that not even light can escape its grasp. These black holes are thought to be the engines that power the brightest objects in the universe, quasars. A quasar is an extremely luminous and distant active galactic nucleus, powered by the accretion of matter into a supermassive black hole. As material falls into the black hole, it heats up and emits enormous amounts of radiation. Quasars are some of the most energetic and mysterious objects in the universe, offering a glimpse into the extreme forces at play in the cosmos. When stars die, their remnants can reveal startling secrets about the universe. Some stars explode as supernovae, while others collapse into neutron stars, objects so dense that a single teaspoon would weigh billions of tons. These neutron stars are packed with matter in an incredibly small space, and their intense magnetic fields and rapid rotation make them fascinating objects of study. Some neutron stars, known as pulsars, emit regular pulses of radiation as they spin, acting like cosmic lighthouses. Studying these stellar remnants allows scientists to probe the most extreme conditions in the universe. There is a part of the universe where the laws of physics are pushed to their limits. This is the realm of quantum mechanics, where particles behave in ways that defy common sense. At the quantum level, particles can exist in multiple places at once, and their behavior can be influenced by observation itself. This strange world is governed by probabilities rather than certainties, and its effects have been confirmed in countless experiments. Though we cannot directly observe quantum phenomena on a human scale, the principles of quantum mechanics govern the very fabric of the universe, shaping everything from atoms to stars. Imagine standing at the edge of the universe, looking back at its earliest moments. What would you see? The faint glow of the cosmic microwave background is the only thing that takes us there. This glow, a remnant from the early universe, is the oldest light we can observe. It carries the memory of the universe's infancy, when it was a hot, dense fog of particles. Over billions of years, this light has stretched and cooled, and today it serves as the most precise tool we have for understanding the universe's birth, offering an eerie snapshot of a time long before stars existed. In the deep, dark heart of the universe, a strange phenomenon bends the very fabric of space-time. This is the realm of black holes, where gravity is so powerful that even light cannot escape. These enigmatic objects grow by pulling in matter from their surroundings, sometimes forming massive accretion disks of gas and dust that whirl around them at incredible speeds. As matter falls in, it heats up, emitting radiation that makes black holes some of the brightest objects in the cosmos. Despite their invisibility, black holes are detectable by their gravitational effects on nearby stars and galaxies. The universe began as a singularity, a point of infinite density where all the forces of nature were united. But how did it all come to be? One idea suggests that before the Big Bang, the universe existed in a state where time and space didn't behave as we know them. The laws of physics break down at the singularity, leaving us with only speculation about what might have happened before the birth of the cosmos. Did our universe emerge from a quantum fluctuation? Is there a cyclical nature to the cosmos, with universes born, die, and then reborn again? These questions remain unanswered. Far from the familiar galaxies and stars we see in the night sky, there is a part of the universe where the rules are twisted and reality becomes strange. In the realm of quantum mechanics, particles can exist in multiple states at once, a bizarre effect known as superposition. This means that, at a quantum level, particles can be both here and there, existing in two places simultaneously until observed. This mysterious phenomenon has been demonstrated in experiments with light and electrons, leading to strange new theories about the interconnectedness of all things in the cosmos. Imagine standing on a distant planet, orbiting a star far away from Earth, watching as a black hole at the center of the galaxy devours everything in its path. Supermassive black holes, with masses millions or even billions of times that of the Sun, lurk at the centers of most galaxies. They exert such intense gravity that they control the entire galaxy, pulling stars into their orbit. Yet, even with their massive size and destructive power, supermassive black holes remain poorly understood as their event horizons prevent us from seeing inside. What happens beyond that point remains one of the greatest mysteries of modern science. We live in a universe that is, at its core, constantly changing. Galaxies collide, stars are born and die, and entire cosmic structures evolve. One of the most fascinating features of the universe is its expansion. Since the Big Bang, the universe has been growing, with galaxies drifting further apart from one another. This expansion is driven by dark energy, a mysterious force that makes up the majority of the universe. As galaxies speed away from us, the space between them stretches, causing the universe to grow larger over time. However, the true nature of dark energy remains one of the most perplexing questions in cosmology. What happens when a star runs out of fuel? The answer lies in a violent event known as a supernova, where a massive star explodes, releasing a tremendous amount of energy. This explosion is so powerful that it can outshine an entire galaxy for a short period. During the explosion, elements heavier than iron are formed, such as gold and uranium, which are scattered throughout space. These elements are essential for the formation of planets, including Earth. And without supernova, the universe would lack the building blocks needed for life. The remnants of the explosion can also leave behind a dense core, forming a neutron star or black hole. In the frozen depths of space, there exists a phenomenon so strange that it seems to defy logic. This is the mysterious world of dark matter, a form of matter that we cannot directly observe, but which exerts a powerful influence on the universe. Dark matter does not emit or absorb light, making it invisible to telescopes. Yet, its gravitational effects are felt across the cosmos, particularly in the way galaxies move. Scientists believe that dark matter makes up about 27% of the universe, but its true nature is still a mystery. What is it made of? Could it be a completely new form of matter, completely different from anything we've ever encountered? The birth of a star is a slow, delicate process that takes millions of years to unfold. It begins with a cloud of gas and dust, known as a nebula, which collapses under its own gravity. As the material falls inward, it heats up and forms a dense core. Eventually, the pressure becomes high enough for nuclear fusion to begin, and a star is born. This star will shine brightly for billions of years, balancing the inward pull of gravity with the outward pressure from the fusion in its core. Over time, the star will age and eventually exhaust its fuel, ending its life in a spectacular way, either as a white dwarf, a neutron star, or a black hole. Could the stars in the sky be harboring worlds just like ours? The discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding of the universe. Some of these exoplanets are remarkably similar to Earth, with similar sizes, temperatures, and compositions. Many are located in their star's habitable zone, the region where conditions might allow liquid water to exist. This discovery raises the exciting possibility that life could exist on other planets, potentially in ways we have yet to fully understand. The study of exoplanets is just beginning, and the search for alien worlds is far from over. There is a place in the universe where space itself is stretched and twisted, where the fabric of reality bends and warps under the influence of massive objects. This is the world of gravitational lensing, where light from distant stars and galaxies is bent around a massive object, like a galaxy, cluster, or black hole. This effect can magnify and distort the light, allowing astronomers to peer deeper into the universe than ever before. Gravitational lensing has provided valuable insights into the distribution of dark matter and the large-scale structure of the cosmos, giving us a unique way to study the universe's most mysterious components. The universe is a cosmic symphony, with every galaxy, star, and planet playing its part in a grand dance. But within this dance, there are hidden forces that shape the motion of everything around us. One of the most influential forces in the universe is gravity. It governs the movement of celestial bodies, from the orbits of planets around stars to the collision of entire galaxies. Gravity also dictates the formation of cosmic structures, including black holes and galaxy clusters. It is the force that binds the universe together, and yet, despite its importance, gravity remains the least understood of the fundamental forces. Imagine a star so massive that it collapses in on itself, creating a black hole. This is the fate of the most massive stars in the universe, which end their lives in a violent explosion known as a supernova. The core of the star collapses into an incredibly dense point, and gravity becomes so strong that not even light can escape. The result is a black hole, an object so dense that it warps space-time itself. Once matter falls into a black hole, it is lost forever, unable to escape the powerful grip of its gravity. There is a phenomenon in the universe that can stretch light and space-time itself. This is known as gravitational time dilation, where time moves more slowly in stronger gravitational fields. If you were near a black hole, for example, time would pass much more slowly for you than for someone far away from it. This effect, predicted by Einstein's theory of relativity, has been confirmed through experiments with atomic clocks. In the future, this principle could have implications for space travel, as astronauts traveling near massive objects like black holes could experience time differently than those on Earth. The universe is vast, and its scale is almost beyond comprehension. The largest structures in the universe are galaxy clusters, groups of galaxies bound together by gravity. These clusters contain hundreds or even thousands of galaxies, and their combined mass is so immense that they warp the fabric of space-time itself. Some galaxy clusters are so massive that they create gravitational lenses, bending the light from galaxies behind them and allowing us to observe distant objects that would otherwise be invisible. These clusters are not static. They are constantly evolving, merging with other clusters and slowly growing over time. Do you ever wonder what happens to time when we reach the speed of light? According to Einstein's special theory of relativity, as an object approaches the speed of light, time begins to slow down for it relative to an observer. This effect, known as time dilation, means that astronauts traveling at near light speeds would age much more slowly than people on Earth. Although we cannot travel at such speeds yet, this principle has been proven experimentally with particles moving close to light speed. In the distant future, time travel might be possible, but only under extreme and mind-bending conditions. Deep in the heart of the cosmos, there are places where gravity is so intense that it creates entire voids in space. These regions, known as black holes, are not just powerful objects. They are gateways to understanding the fundamental workings of the universe. Black holes distort space and time, pulling in everything that comes too close. Once something crosses the event horizon, there's no escape. The matter inside these cosmic prisons is crushed into an infinitely dense point, creating a singularity. What happens inside this point remains a mystery as our current laws of physics break down. The future of the universe could be a cold, dark, and lonely place. As galaxies continue to drift further apart due to the expansion of space, the universe will eventually become so spread out that stars will burn out, leaving only remnants of cosmic history. This scenario, known as the Big Freeze, suggests that the universe will grow increasingly colder over trillions of years, with galaxies fading into the distance, their stars long since extinguished. With dark energy accelerating the expansion, the universe's fate seems to be a slow, gradual drift toward emptiness, a cosmic quiet. If you could travel back in time, the earliest moments of the universe would appear unrecognizable. After the Big Bang, the universe was a hot, dense soup of particles. During the first few minutes, nuclear reactions took place, creating the lightest elements like hydrogen, helium, and lithium. These elements, formed in the first few minutes after the Big Bang, are the building blocks for stars, galaxies, and, eventually, life itself. The traces of these primordial elements can still be observed in the oldest stars, offering us a glimpse into the universe's earliest history and its creation story. Have you ever wondered how the vast web of galaxies that make up the universe was formed? The answer lies in the cosmic density fluctuations that arose in the early universe. Tiny differences in the distribution of matter led to the formation of dense regions that eventually became the first stars and galaxies. These structures, known as the cosmic web, span vast distances and are interconnected by vast cosmic filaments of gas and dark matter. Over billions of years, these filaments and clusters of galaxies have evolved, creating the intricate cosmic landscape we observe today. In the deepest parts of space, there exists a phenomenon that bends light and distorts the view of the universe itself. This is gravitational lensing, a fascinating effect where massive objects like galaxy, clusters, or black holes warp space-time so much that they magnify and distort the light from objects behind them. This effect allows scientists to study distant galaxies and cosmic structures that would otherwise be hidden from view. Gravitational lensing also provides clues about the distribution of dark matter, which cannot be seen directly, but influences the light in these distant regions. The story of stars is one of both creation and destruction. Stars are born in dense clouds of gas and dust, where gravity pulls material together to form a nuclear furnace. Over millions or billions of years, stars burn their fuel, creating heavier elements in the process. When a star runs out of fuel, it dies, often in a spectacular explosion known as a supernova. During this explosion, elements like gold, silver, and uranium are created and scattered across space. These elements are then incorporated into new stars, planets, and even life itself, creating a cosmic cycle of creation and rebirth. Did you know that there is a force in the universe that we can't directly detect, but which influences the motion of galaxies and stars? This invisible force is known as dark matter, and it makes up about 27% of the universe. Although we can't see dark matter, we know it exists because of its gravitational effects on visible matter. Dark matter doesn't emit light or energy, making it undetectable by conventional telescopes. Yet, its presence is inferred by the way galaxies move and how light bends around them. Unraveling the mysteries of dark matter is one of the most exciting challenges in modern astrophysics. As the universe ages, the stars we see today will gradually fade into the background, their light eventually extinguished. Stars like our Sun will burn out after billions of years, leaving behind remnants such as white dwarfs, neutron stars, or even black holes. These stellar remnants may continue to influence the surrounding space for eons. In the case of black holes, their gravitational pull will keep matter and energy trapped forever. White dwarfs, on the other hand, will slowly cool and fade into darkness, marking the end of their stellar journey. These remnants will form the cosmic landscape for trillions of years after the stars have gone. The birth of a star is a magnificent yet slow process. In a nebula, clouds of gas and dust scattered across space, gravity begins to pull the material together. As the cloud collapses, it heats up, and at the core, a new star forms. This process takes millions of years, with the star gradually growing hotter and more luminous. Once nuclear fusion begins in the core, the star enters its main sequence phase, where it will stay for most of its life, shining brightly and creating the elements that will later form planets and even life itself. The life of a star is an intricate balance between gravity and fusion. In the far future, the fate of the universe may be sealed by dark energy, the mysterious force driving the accelerated expansion of the cosmos. The discovery of dark energy in the late 20th century fundamentally changed our understanding of the universe. While dark energy makes up about 68% of the cosmos, its nature remains unknown. It causes galaxies to move away from one another at an increasing rate, suggesting that the universe will continue to expand forever. This expansion could eventually lead to a state of isolation, where galaxies are so far apart that they become invisible to each other, creating a universe of lonely, distant stars. What if time, as we understand it, is not an absolute concept, but one that can be bent, stretched, and warped? In the presence of strong gravitational fields, such as those near black holes or in the early universe, time behaves differently. Time dilation, as predicted by Einstein's theory of relativity, causes time to pass more slowly in strong gravitational fields. This effect has been confirmed in numerous experiments, including those with atomic clocks on satellites. In practical terms, astronauts traveling near massive objects would age more slowly than people on Earth, giving rise to fascinating possibilities for future space exploration. Galaxies are not solitary islands in the vastness of space. Instead, they are part of larger cosmic structures bound together by gravity. These structures, known as galaxy clusters, contain hundreds or even thousands of galaxies, all held together by the gravitational pull of dark matter. The galaxies in a cluster can interact with each other, sometimes colliding and merging, leading to the formation of new stars and even supermassive black holes. The study of galaxy clusters offers valuable insight into the large-scale structure of the universe, revealing the hidden influence of dark matter and the forces that shape the cosmos. As the universe continues to expand, galaxies grow further apart, but the cosmic web that connects them remains intact. This web of galaxies, dark, matter, and gas forms an intricate structure that spans vast distances across the cosmos. The study of this web, known as the cosmic web, reveals how galaxies are interconnected by dark matter and how they evolve over time. The cosmic web is constantly changing, with galaxies merging, forming new stars, and creating the building blocks for future galaxies. Understanding this grand structure is key to unlocking the mysteries of the universe's past, present, and future. Is there an end to the universe, or does it continue forever, stretching outward into infinity? The expansion of the universe is accelerating, not slowing down as once thought. Dark energy, a force that is not yet fully understood, is driving this expansion. As galaxies move further apart, the universe grows colder and stars burn out, leaving only the faint glow of distant galaxies. One theory, called the Big Freeze, suggests that the universe will continue to expand indefinitely until all matter is spread thinly across the vastness of space, with temperatures dropping so low that no stars or life can exist. In the vast empties of space, there are regions so cold and empty that they may never have been touched by a star. These areas, known as cosmic voids, are vast expanses of space where few galaxies exist. Void regions can stretch across hundreds of millions of light years, making up a significant portion of the universe's structure. These voids may seem empty, but they play an important role in the universe's evolution. Galaxies tend to be clustered in the areas surrounding these voids, and their distribution helps shape the large-scale structure of the cosmos. Deep within galaxies, there exists an invisible force that shapes everything around it. This force, known as dark matter, is thought to make up around 27% of the universe's total mass. Despite being invisible and undetectable by traditional means, dark matter exerts a profound influence on the motion of galaxies and galaxy clusters. Its gravitational pull keeps galaxies from flying apart, and its distribution across the universe is key to understanding the large-scale structure of the cosmos. While scientists are still unsure what dark matter is made of, its presence is undeniable. If you were to travel to the outer reaches of the universe, you would find that time itself seems to stretch out, slowly fading as you approach the cosmic horizon. This strange effect is a result of the expansion of the universe. The galaxies at the edges of the observable universe are moving away from us at speeds that exceed the speed of light. This stretching of space causes the light from these galaxies to redshift, making them appear dimmer and less visible. Over time, these galaxies will fade from view, becoming unreachable as the universe continues to expand. In the early moments of the universe, the conditions were extreme, with temperatures and pressures beyond our comprehension. The first few minutes after the Big Bang were crucial in shaping the universe's future. In this brief time, the universe cooled enough for the first atomic nuclei to form, giving birth to the simplest elements: hydrogen, helium, and a small amount of lithium. These elements would go on to form the first stars and galaxies, creating the foundation for everything we see in the cosmos today. Without these early moments, the universe would have remained a hot, chaotic soup of particles. As the universe continues to expand, galaxies are drifting farther and farther apart. This expansion, driven by dark energy, is accelerating, causing the space between galaxies to stretch. Over billions of years, This will lead to a future where galaxies will become isolated, with no observable neighbors. In this scenario, the universe would eventually become a place of isolated stars, unable to interact or form new galaxies. This big freeze scenario suggests that the cosmos will grow increasingly cold and dark, eventually reaching a state where no new stars or life can form. One of the most intriguing phenomena in the universe is the existence of neutron stars, the remnants of massive stars that have exploded as supernovae. These dense objects are packed with matter so tightly that a single cubic centimeter would weigh as much as a mountain on Earth. Neutron stars are incredibly hot and emit powerful radiation, including X-rays and gamma rays. Some neutron stars, known as pulsars, spin rapidly, emitting beams of radiation at regular intervals, acting like cosmic lighthouses. The study of these stars offers insight into the extreme conditions that govern the universe. What happens when two massive galaxies collide? In the vastness of space, such collisions are not uncommon, and they often lead to spectacular events. When galaxies merge, their stars don't collide, since stars are separated by vast distances. But their gas clouds interact, triggering the formation of new stars. These galactic collisions also cause the central supermassive black holes to spiral toward one another, eventually merging to form an even larger black hole. These events can release enormous amounts of energy, leading to the creation of some of the brightest and most energetic phenomena in the universe. The universe is filled with bizarre and exotic objects that defy our understanding of reality. One such object is the quasar, a supermassive black hole at the center of a distant galaxy. Quasars are incredibly bright and emit vast amounts of radiation, outshining entire galaxies. The energy produced by a quasar comes from the material being pulled into the black hole's accretion disk. As this material spirals inward, it heats up and emits powerful radiation. Quasars are thought to be powered by the immense gravitational forces of supermassive black holes, and their study offers a glimpse into the most energetic processes in the cosmos. The universe's expansion is not only a simple stretching of space, but also a key to understanding the fate of the cosmos. The discovery of the universe's accelerating expansion, driven by dark energy, has radically changed our view of the universe's future. If this acceleration continues, galaxies will eventually move so far apart that they will be unreachable, even in principle. The Big Freeze scenario, in which stars burn out and galaxies drift into isolation, is one possible outcome. This suggests that the universe will continue to grow colder and darker over billions of years, eventually reaching a state where no new stars or life can emerge. Stars, like all living things, have a lifespan. Their birth and death are intimately connected to the elements they create. The life cycle of a star begins with the fusion of hydrogen atoms in its core, a process that releases immense amounts of energy. This energy creates the light and heat that we see as starlight. As the star ages, it begins to fuse heavier elements like helium and carbon. When a star exhausts its fuel, it can no longer support itself against the pull of gravity, leading to its death in a dramatic supernova explosion. The elements formed in this explosion enrich the surrounding space, laying the groundwork for new stars and planets. Far beyond the solar system, astronomers have discovered thousands of planets orbiting distant stars. These exoplanets, as they are known, come in many shapes and sizes. Some are similar to Earth, with rocky surfaces and potential atmospheres that could support life. Others are gas giants like Jupiter, with immense atmospheres and swirling storms. The discovery of exoplanets has sparked a renewed interest in the search for extraterrestrial life. Scientists wonder whether any of these distant worlds could harbor conditions suitable for life. Each new exoplanet discovered brings us one step closer to understanding the diversity of planets in our galaxy. As you gaze up at the stars, you might be seeing light that has traveled across vast stretches of space and time. Some of the stars you see are not as they are today, but as they were millions or even billions of years ago. Light takes time to travel across the cosmos, and as a result, we are always seeing the past when we look at distant stars. This delay allows us to look back in time, observing the evolution of stars, galaxies, and the universe itself. It's a reminder that the universe is both vast and dynamic, constantly changing before our eyes. In the cold, dark void between galaxies, there exists an invisible web that holds the universe together. This web, known as the cosmic web, is made up of vast filaments of dark matter, gas, and galaxies that stretch across billions of light years. These filaments create the structure of the universe, linking galaxies together in a giant network. At the intersections of these filaments, the densest regions form galaxy clusters, while the empty spaces in between are known as voids. Understanding the cosmic web is key to understanding the large-scale structure of the universe and the forces that govern it. As the universe expands, the galaxies are being stretched apart, and this stretching of space has a profound effect on the light traveling through it. Known as redshift, this phenomenon occurs when light from distant galaxies is stretched to longer wavelengths as the universe expands. The farther away a galaxy is, the more its light is redshifted. This effect allows astronomers to measure the rate of expansion of the universe and provides clues about the age and size of the cosmos. It also offers a glimpse into the universe's past, as the light we observe today was emitted billions of years ago. What if the laws of physics we take for granted are not the same everywhere in the universe? Some theories suggest that the fundamental constants of nature, like the speed of light or the strength of gravity, may vary across space and time. This idea, known as variable constants, challenges our understanding of the universe and raises the possibility that the laws governing distant regions of space might be different from those we observe on Earth. Such variations could have profound implications for the nature of reality itself, suggesting a universe that is far more mysterious and complex than we imagine. In the distant future, our Sun will no longer be the life-giving star we know today. As it ages, it will exhaust its nuclear fuel and expand into a red giant, swallowing Mercury, Venus, and possibly even Earth. During this phase, the Sun will shed its outer layers, creating a nebula of gas and dust. What remains will be a dense core, a white dwarf, which will slowly cool over billions of years. This transformation is part of the natural life cycle of stars like our Sun, and it marks the end of its journey through the cosmos. The search for life beyond Earth has driven scientists to look for planets that might harbor conditions similar to those on our own world. One of the most important factors in this search is the presence of liquid water, as water is considered essential for life. Many exoplanets, planets orbiting stars outside our solar system, are located in what is known as the habitable zone, the region around a star where temperatures are just right for liquid water to exist. The discovery of these potentially habitable worlds has ignited the possibility that life could exist elsewhere in the universe, waiting to be discovered. At the heart of many galaxies lies a supermassive black hole, an object so dense that not even light can escape its gravitational pull. These black holes can be millions or even billions of times more massive than our Sun, and they exert an enormous influence on their surrounding galaxies. Matter that falls into a black hole is swallowed up, but not without first emitting intense radiation as it is heated in the accretion disk. These radiation emissions can make the center of a galaxy the brightest part of the entire universe. The study of supermassive black holes offers valuable insights into the behavior of matter under extreme conditions. If you could travel to the center of a galaxy, you would find a place where stars, gas, and dark matter collide in a swirling dance around a supermassive black hole. The gravitational forces at play in these galactic centers are so intense that they cause everything around them to move at incredible speeds. This high-speed motion creates immense heat and radiation, which can be detected across vast distances. In some galaxies, the activity around the central black hole can be so energetic that it outshines the entire galaxy. These active galactic nuclei are among the brightest and most energetic objects in the universe. Our understanding of the universe is largely based on the concept of space-time, the four-dimensional fabric that combines space and time into a unified whole. According to Einstein's theory of relativity, massive objects like stars and planets cause space-time to curve, and this curvature is what we experience as gravity. The greater the mass of an object, the more it distorts space-time. This effect is most noticeable near black holes, where the curvature becomes so extreme that not even light can escape. Space-time is not just a static backdrop to the universe. It is an active participant in shaping the cosmos. The mysteries of the universe often lie hidden in the most unexpected places. Take, for example, the cosmic microwave background radiation, a faint glow that permeates the entire universe. This radiation is a remnant of the Big Bang, the explosion that gave birth to the universe. It is the oldest light we can detect, providing a snapshot of the universe as it was just 380,000 years after the Big Bang. By studying this radiation, scientists can learn about the early conditions of the universe, including its temperature, density, and composition, giving us a window into the origins of the cosmos. Have you ever wondered about the strange behavior of light near black holes? As light passes close to a black hole, it is bent and stretched by the intense gravitational forces. This phenomenon, known as gravitational lensing, allows us to observe objects that are otherwise hidden behind a black hole. When light is bent in this way, it can reveal the hidden structures of the universe, such as distant galaxies or even the presence of dark matter. Gravitational lensing is a powerful tool for astronomers, enabling them to study the universe's most mysterious and distant objects. The concept of a multiverse, an infinite number of parallel universes, has fascinated scientists and philosophers alike. While we can only observe the universe in which we live, some theories suggest that there could be other universes, each with its own set of physical laws. These universes might exist in different dimensions, or they might be entirely disconnected from our own. The idea of the multiverse challenges our understanding of reality and raises profound questions about the nature of existence. Could our universe be just one bubble in a vast cosmic ocean of universes? In the early universe, the first atoms began to form, cooling the hot, dense plasma that filled the cosmos in the aftermath of the Big Bang. This process, known as recombination, occurred about 380,000 years after the Big Bang, when the temperature of the universe dropped enough for electrons to combine with protons and form neutral hydrogen atoms. This allowed light to travel freely for the first time, giving birth to the cosmic microwave background radiation. These first atoms are the building blocks for all the matter in the universe, laying the foundation for the stars, planets, and galaxies to come. In the vast darkness of space, the supernova explosion is one of the most spectacular events in the universe. When a massive star reaches the end of its life, it undergoes a cataclysmic collapse, triggering a massive release of energy. This explosion can outshine an entire galaxy, and for a short time, a single supernova can be brighter than all the stars in the galaxy combined. During the explosion, elements heavier than iron are formed in the intense heat, including gold, uranium, and platinum. These newly formed elements are then scattered across space, enriching the cosmos with the building blocks for new stars, planets, and even life. The theory of relativity proposed by Albert Einstein revolutionized our understanding of space and time. It introduced the idea that space and time are not separate entities, but are interconnected in a four-dimensional fabric called space-time. Massive objects like stars and planets cause this fabric to curve, and this curvature is what we experience as gravity. The stronger the gravitational pull of an object, the more it bends space-time. This bending also has profound effects on the passage of time, leading to phenomena like time dilation, where time moves more slowly near massive objects such as black holes. The farthest reaches of the universe are not only a place of isolation, but also a region of intense activity. One of the most fascinating discoveries in modern astronomy is the observation of gamma-ray bursts, some of the most powerful explosions in the cosmos. These bursts release more energy in a few seconds than the Sun will emit over its entire lifetime. Gamma-ray bursts are believed to be caused by the collapse of massive stars or the collision of neutron stars. The energy from these explosions can travel across the universe, offering a glimpse into some of the most extreme environments in space. In the dense cores of galaxies, powerful forces are at work. Supermassive black holes lurk at the center of most large galaxies, their immense gravity influencing everything around them. These black holes can weigh millions or even billions of times more than our Sun, and their gravitational pull extends over vast distances. As matter falls into a black hole, it heats up and emits powerful radiation, often making the center of the galaxy the brightest part of the entire universe. The study of supermassive black holes provides valuable insight into the structure and evolution of galaxies. In a distant future, long after the last stars have burned out, the universe will enter a state of eternal darkness and cold. This scenario, known as the Big Freeze, suggests that the universe will continue to expand forever, eventually leaving galaxies isolated from each other. As galaxies drift further apart, the stars within them will burn out, and the universe will be left with only remnants of its former glory: white dwarfs, neutron stars, and black holes. This chilling fate represents the slow death of the cosmos, where even the most energetic processes will fade into nothingness. The idea of a multiverse, multiple parallel universes, has captivated the imaginations of scientists and theorists for years. While our universe appears to be a single, isolated entity, some theories suggest that there could be countless other universes, each with its own set of physical laws. These universes might be similar to our own, or they might be radically different, with entirely different forms of matter and energy. The idea of a multiverse challenges our understanding of reality and opens up the possibility that our universe is just one small corner of a vast and complex cosmic landscape. As we look up at the night sky, we see only a small fraction of the stars in the universe. The Milky Way, our home galaxy, contains an estimated 100 to 400 billion stars, but it is just one of billions of galaxies scattered across the cosmos. The light from distant galaxies takes millions or even billions of years to reach us, meaning that when we observe these galaxies, we are seeing them as they were long ago. The study of these distant galaxies allows astronomers to understand the early universe and its evolution, providing a window into the distant past of the cosmos. In the eerie silence of space, there are places where time itself seems to stand still. Black holes are regions where space and time become so warped that the normal rules of physics no longer apply. At the event horizon, the point beyond which nothing can escape, time slows down relative to an outside observer. For someone falling into a black hole, time would seem to stretch out indefinitely, and they would never actually reach the event horizon. What happens beyond the event horizon, however, is unknown. Once something crosses that point, it is lost to the black hole forever. The study of exoplanets, planets orbiting stars outside our solar system, has revealed a staggering diversity of worlds. Some exoplanets are similar to Earth, with rocky surfaces and the potential for liquid water. Others are gas giants like Jupiter, with massive atmospheres and violent weather patterns. A few exoplanets are even located in the habitable zone of their parent stars, where temperatures are just right for liquid water to exist. The discovery of these distant planets has sparked new questions about the potential for life beyond Earth, leading to a renewed interest in the search for extraterrestrial life. The expansion of the universe is not just a theoretical concept, it is an observable phenomenon. By measuring the redshift of light from distant galaxies, scientists have determined that the universe has been expanding since the Big Bang. The rate of this expansion is increasing due to the influence of dark energy, a mysterious force that makes up the majority of the universe's energy content. This accelerating expansion means that galaxies are moving further apart at an ever-increasing rate. Over time, this will lead to a future where galaxies become isolated and the universe becomes colder and darker. The birth of a star is a process that unfolds over millions of years. It begins in a cloud of gas and dust, known as a nebula, which collapses under the force of gravity. As the material falls inward, it heats up, and eventually nuclear fusion begins in the core. This marks the birth of a new star. Over the course of its life, the star will burn through its fuel, creating heavier elements in the process. When it exhausts its fuel, the star will die, and depending on its mass, it may end its life as a white dwarf, a neutron star, or a black hole. Dark matter is one of the greatest mysteries in the universe. Although we cannot see it directly, Scientists know it exists because of its gravitational effects on visible matter. Dark matter makes up about 27% of the universe, but it does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred by the way galaxies move and how light bends around them. Some scientists believe that dark matter could be made of exotic particles that interact very weakly with ordinary matter. Understanding dark matter is one of the key challenges in modern cosmology. Out in the depths of space, there's a phenomenon so strange that it stretches the very fabric of space-time. This phenomenon is called gravitational wave, and it occurs when massive objects like black holes or neutron stars accelerate and collide. These collisions send ripples through space-time, like waves on a pond, which travel outward at the speed of light. These waves were first detected in 2015, confirming a major prediction of Einstein's general theory of relativity. Gravitational waves offer a new way to observe the universe, opening a window to some of the most extreme and violent events in space. At the heart of every galaxy lies a supermassive black hole, an object so dense that its gravitational pull prevents even light from escaping. These black holes can be millions or billions of times more massive than the Sun, and can influence the entire galaxy around them. They are thought to grow by accreting matter from their surroundings, including gas, dust, and even stars. As material falls into the black hole, it heats up, emitting powerful radiation that can outshine the entire galaxy. The study of these supermassive black holes helps us understand the dynamics of galaxies and their evolution. Did you know that the universe has a memory? This memory is encoded in the cosmic microwave background radiation, a faint glow left over from the Big Bang. This radiation is the oldest light in the universe, and it carries information about the conditions of the universe when it was just 380,000 years old. By studying the cosmic microwave background, scientists can learn about the universe's early moments, including its temperature, density, and the distribution of matter. This radiation offers a snapshot of the universe as it was before stars, galaxies, and even light itself began to take shape. As stars age, they undergo a transformation, eventually reaching the end of their lives in a dramatic explosion known as a supernova. The energy released during a supernova is so immense that it can briefly outshine an entire galaxy. Supernovae are responsible for creating some of the heaviest elements in the universe, including gold, uranium, and platinum. These elements are scattered throughout space, enriching the interstellar medium and forming the building blocks for new stars, planets, and even life. The death of a star is as important as its birth, creating the raw materials for the next generation of cosmic objects. In the early universe, there was no light. The first few 100,000 years after the Big Bang were a time of darkness, as the universe was too hot and dense for light to travel freely. But as the universe cooled, the first atoms began to form, and the first light, known as the cosmic dawn, was emitted. This light, which we can still observe today in the form of the cosmic microwave background, marks the point at which the universe became transparent to light. Study of this primordial light allows scientists to peer into the universe's infancy and learn about its earliest stages. In the empty expanses of space, there are vast regions known as cosmic voids, where galaxies are few and far between. These voids can stretch across hundreds of millions of light years, forming the largest known structures in the universe. Despite their emptiness, voids are crucial for understanding the large-scale structure of the cosmos. They are shaped by the distribution of dark matter and are surrounded by the cosmic web, which is made up of galaxies and clusters of galaxies. Studying voids provides insight into how the universe has evolved and how matter is distributed across vast distances. Beyond the familiar stars and planets, there exists a whole class of strange, exotic objects that defy our conventional understanding of the universe. One of the most fascinating of these objects is the neutron star, which is formed when a massive star undergoes a supernova explosion. Neutron stars are incredibly dense, with a single cubic centimeter of their material weighing as much as an entire mountain. They are so dense that the force of gravity on their surfaces is billions of times stronger than Earth's. Neutron stars also emit beams of radiation, which can be observed as pulsars, acting like cosmic lighthouses. Have you ever wondered how galaxies form and evolve? The process begins in the early universe, when small fluctuations in the density of matter led to the formation of the first stars and galaxies. These early galaxies merged and collided over billions of years, growing larger and more complex. In the centers of many of these galaxies, supermassive black holes formed, influencing the growth of the galaxies around them. The study of galaxy formation helps astronomers understand the forces that have shaped the universe, including the roles played by gravity, dark matter, and the mysterious dark energy. At the edge of our observable universe, there exists a boundary known as the cosmic horizon. Beyond this horizon, the universe continues to expand, but the light from objects beyond this point will never reach us. This means that we can never observe or study anything beyond the cosmic horizon. As the universe continues to expand at an accelerating rate, more and more objects will cross this boundary, making them forever unreachable. The cosmic horizon marks the limits of our knowledge and serves as a reminder of the vastness and mystery of the universe. One of the most mysterious aspects of the universe is the presence of dark energy, a force that is accelerating the expansion of the cosmos. Dark energy makes up about 68% of the universe, yet we know very little about it. It is thought to have existed since the early moments of the universe, but its exact nature remains a profound mystery. Some scientists believe that dark energy could be a property of space itself, causing it to expand. Understanding dark energy is one of the biggest challenges in modern cosmology, and its discovery could reshape our understanding of the universe's fate. If you could peer into the farthest reaches of space, you might witness the birth of a new galaxy. Galaxies are not static objects, they are constantly evolving. In the early universe, galaxies were smaller and more irregular, but over billions of years, they merged and grew into the massive, spiral and elliptical galaxies we see today. The study of galaxy evolution helps us understand the complex processes that govern the growth of these cosmic structures, including the role of dark matter, the influence of supermassive black holes, and the ongoing interplay between gravity, gas, and stars. Our understanding of the universe has been shaped by the discovery of cosmic radiation, specifically the cosmic microwave background. This faint radiation is a remnant of the Big Bang and provides a snapshot of the universe just 380,000 years after its birth. The study of this radiation has given us profound insights into the early universe, allowing scientists to measure its temperature, density, and composition. The cosmic microwave background also serves as a key piece of evidence supporting the Big Bang theory, which proposes that the universe began as an incredibly hot and dense point and has been expanding ever since. In the eerie, starry abyss of space, there exists a mysterious phenomenon that warps everything in its path: black holes. These objects, which form from the remnants of massive stars, possess such strong gravitational fields that not even light can escape their grasp. At their center lies the event horizon, a point of no return. Anything that crosses this boundary is forever lost to the black hole's singularity. Despite their invisible nature, black holes can be detected by their effects on nearby stars and gas, and they are thought to be key players in shaping the structure of galaxies. Beyond our solar system, there exists a vast and seemingly endless ocean of planets, many of which could harbor life. Scientists have discovered thousands of exoplanets, planets that orbit stars outside of our solar system. Some of these planets are in the habitable zone, where conditions may be just right for liquid water to exist. The study of exoplanets has opened up new possibilities in the search for extraterrestrial life, with astronomers now looking for signs of biosignatures, chemical markers that could indicate the presence of life on distant worlds. In the cold voids of space, there are regions where the very laws of physics seem to be bent and twisted. This strange behavior is often observed near black holes, where the intense gravitational forces cause the fabric of space-time to curve. This phenomenon, known as gravitational lensing, occurs when light from distant objects is bent by the gravity of a massive object, such as a galaxy or a black hole. Gravitational lensing allows astronomers to observe distant galaxies and dark matter that would otherwise be hidden from view. It is one of the most powerful tools for studying the cosmos. Have you ever wondered what the universe was like in its infancy? The early universe, just moments after the Big Bang, was an incredibly hot and dense place. During this time, particles like quarks and electrons were constantly interacting, creating a chaotic environment. As the universe cooled, these particles began to combine, forming the first atoms. This period, known as the recombination era, was crucial in shaping the future of the cosmos, as it allowed light to travel freely for the first time, leading to the creation of the cosmic microwave background, the faint glow we can still observe today. In the farthest reaches of space, galaxies are not isolated. They are part of vast clusters bound together by the force of gravity. These galaxy clusters are some of the largest structures in the universe, containing hundreds or even thousands of galaxies. The gravitational pull within these clusters is so strong that it can bend light, a phenomenon known as gravitational lensing. Clusters of galaxies are also home to dark matter, which can only be detected by its gravitational effects. Studying these clusters helps astronomers understand the distribution of dark matter and the large-scale structure of the universe. Some of the most extreme environments in the universe exist in the cores of stars. These stellar furnaces generate enormous amounts of energy through nuclear fusion, turning hydrogen into helium and releasing vast amounts of light and heat. As a star ages, it begins to fuse heavier elements like carbon, oxygen, and iron. Once a star exhausts its fuel, it can no longer support itself against gravity, leading to its death. Depending on its mass, a star may end its life as a white dwarf, a neutron star, or a black hole, each of which represents a different fate for the remnants of the star. In the uncharted corners of space, some galaxies are hurtling toward one another on a collision course that will forever change their shape. These galactic mergers are common in the universe and are thought to play a crucial role in the formation of larger galaxies. When galaxies collide, their stars usually pass by one another without direct contact due to the vast distances between them. However, their gas clouds interact, triggering the formation of new stars. The merger of two supermassive black holes at the center of these galaxies can also release enormous amounts of energy, creating some of the most spectacular cosmic events. In the vast emptiness of space, there exists a force so subtle yet so powerful that it shapes the entire universe. This force, called dark energy, is believed to account for roughly 68% of the universe's total energy content. Dark energy is responsible for the accelerated expansion of the universe, pushing galaxies further apart at an ever-increasing rate. Despite being one of the most dominant forces in the universe, dark energy remains a mystery. Its existence was first inferred in the late 1990s, and scientists are still working to understand its nature and how it will influence the universe's ultimate fate. Have you ever looked up at the stars and wondered how many of them have planets of their own? Scientists estimate that most stars in the Milky Way galaxy have at least one planet orbiting them, and many of these planets could be similar to Earth. These so-called Earth-like exoplanets are found in the habitable zone of their parent stars, where conditions might be right for liquid water to exist. Some exoplanets may even have atmospheres capable of supporting life. The discovery of these worlds has reignited the search for extraterrestrial life as we ponder whether we are truly alone in the cosmos. At the very beginning of the universe, conditions were so extreme that time and space themselves were in flux. The first moments of the Big Bang were a time of rapid expansion, known as inflation, during which the universe grew exponentially in size in a fraction of a second. This sudden expansion stretched the fabric of space-time, leaving behind the large-scale structures we see today. During this period, the universe cooled rapidly and particles began to form, eventually giving rise to the atoms that would become the building blocks of stars, galaxies, and everything in the universe. The force of gravity is one of the most fundamental forces in the universe, but its effects can vary dramatically depending on where you are. Near massive objects like stars and black holes, gravity is incredibly strong, warping space-time and causing time to slow down relative to distant observers. This phenomenon, known as time dilation, is a direct consequence of Einstein's theory of relativity. It means that if you were to orbit a black hole or live on a planet with intense gravity, time would move more slowly for you than for someone far away from such objects. Across the universe, vast expanses of space remain devoid of stars, galaxies, and even visible matter. These enormous regions, known as cosmic voids, represent the largest structures found within the cosmos. Stretching hundreds of millions of light-years across, voids make up about 80% of the universe's volume. Surprisingly, these voids are not completely empty. They contain low-density gas and dark matter. Void studies provide valuable insights into cosmic expansion, dark matter, and how the universe evolved from its dense beginnings to the more spread-out structure we observe today. A phenomenon known as cosmic inflation took place during the universe's earliest moments, driving an extraordinary expansion within a fraction of a second. This rapid growth stretched space-time to an unimaginable size, smoothing out irregularities and laying the groundwork for all cosmic structures that would follow. Inflation theory provides explanations for uniformity in the cosmic microwave background radiation, offering clues to the universe's early state. It also suggests the possibility of a multiverse, where different regions of space-time could evolve into separate universes with distinct physical properties. Far beyond Earth's atmosphere lies an invisible force that shapes galaxies and holds them together: dark matter. While not directly observable, dark matter can be detected by its gravitational influence on surrounding galaxies. It's thought to make up about 27% of the universe's mass-energy content. Despite extensive studies, scientists still don't know what dark matter is made of, though various theories suggest exotic particles could be involved. It's likely that dark matter played a pivotal role in the formation of galaxies, clumping together under gravity and acting as the scaffolding around which stars and planets later formed. The universe's expansion isn't just a static process, it's accelerating. This acceleration is caused by a mysterious force known as dark energy. First detected in the late 1990s, dark energy is believed to make up around 68% of the universe's energy. It pushes galaxies apart, speeding up the expansion of space itself. This discovery transformed cosmology, forcing scientists to reconsider models of the universe's fate. While we don't yet understand the exact nature of dark energy, it seems poised to play a significant role in determining the ultimate destiny of everything within the cosmos. Have you ever pondered the fate of a dying star? When a star like our Sun reaches the end of its life, it expands into a red giant, shedding outer layers and leaving behind a dense, hot core. This process marks the star's transition into a white dwarf. Over the course of billions of years, the white dwarf gradually cools, becoming a faint ember. Stars with more mass meet a different fate, collapsing under their own gravity and forming neutron stars or black holes. These deaths are as important as the star's births, contributing essential elements for future cosmic generations. Light, as we know it, doesn't travel forever without changing. As light travels through expanding space, it stretches, shifting toward longer wavelengths, a phenomenon known as redshift. This effect is especially noticeable with galaxies far away from us, whose light grows redder the farther they are. This redshift is one of the main tools astronomers use to measure the expansion of the universe. By studying the degree of redshift, scientists can determine the rate at which the universe is expanding and gain a deeper understanding of its age and structure. Stars are born from the chaotic collisions of gas clouds that collapse under gravity. Over millions of years, these clouds compress, heating up until nuclear fusion ignites, marking the birth of a star. This stellar furnace continues to burn hydrogen into helium for billions of years. But a star's life doesn't end there. It evolves through various phases. Depending on its mass, it may end as a white dwarf, a neutron star, or even collapse into a black hole. Stars, during their lifetimes, also create heavier elements that will later form planets and, possibly, life itself. As galaxies age, they undergo transformations that shape their appearance and behavior. Initially, galaxies form from smaller clumps of gas and dust that come together under gravity. Over billions of years, these clumps merge and evolve into larger galaxies. Some galaxies develop into spirals, while others become elliptical or irregular. The forces at play during these mergers and interactions often trigger bursts of star formation, reshaping the galaxy's structure. Understanding this evolution helps astronomers uncover the processes that have led to the formation of galaxies like our Milky Way. The energy and heat produced by stars is essential for life as we know it. Within a star's core, nuclear fusion turns light elements, like hydrogen, into heavier ones, releasing enormous amounts of energy in the process. This energy radiates outward, heating the star's outer layers and providing the light that makes it visible. As stars age, they begin to fuse heavier elements like carbon and oxygen. Eventually, when a star exhausts its fuel, it ends its life in a dramatic event, whether it's a supernova, a collapse into a black hole, or a slow fade into a white dwarf. Space-time isn't as rigid as it might seem. According to Einstein's theory of general relativity, massive objects like stars and planets cause space-time to warp. This curvature is what we experience as gravity. The greater the mass of an object, the more it bends the fabric of space-time around it. This bending has fascinating consequences, such as time dilation. Time moves slower near objects with intense gravitational fields, such as black holes, creating a fascinating difference between what an observer experiences close to a black hole and what someone far away experiences. The universe is full of things we can't see, yet we know they exist. One of these invisible forces is dark matter, which accounts for about 27% of the universe's mass. Though it doesn't emit light or energy, we can infer its presence by observing its gravitational effects on visible matter. Dark matter's role in the formation of galaxies is crucial. It acts as the glue holding galaxies together, preventing them from flying apart due to their rotational speeds. Without dark matter, the universe would be an entirely different place, less structured, with galaxies possibly unable to form. Hidden within the cold expanse of space are countless objects that defy the imagination. Neutron stars are some of the densest objects in the universe, formed when a massive star explodes in a supernova. These stars are so compact that their matter is packed to the extreme, with a single cubic centimeter of neutron star material weighing as much as an entire mountain. A neutron star's surface gravity is so intense that it warps space-time around it, and many of these stars spin incredibly fast, emitting regular pulses of radiation that can be detected across vast distances. Our universe is expanding, but this expansion isn't happening evenly. Galaxies are speeding away from each other, and the farther away they are, the faster they move. This observation led to the discovery of the universe's accelerating expansion, which is driven by a mysterious force known as dark energy. While dark energy remains one of the greatest enigmas in modern cosmology, scientists know that it is pushing galaxies apart at an ever-increasing rate. This cosmic acceleration challenges existing theories about the future of the universe, suggesting it may eventually become an eternal, dark and cold place. At the heart of every massive galaxy, there lies a supermassive black hole whose immense gravitational pull governs the galaxy's structure and evolution. These cosmic giants can be millions or even billions of times the mass of the Sun. As matter spirals into the black hole, it heats up, releasing powerful radiation that can outshine the combined light of entire galaxies. Despite their intimidating nature, These supermassive black holes are crucial to the formation and behavior of galaxies, playing a key role in how stars and other cosmic structures evolve. One of the most perplexing features of space is how it behaves under extreme conditions. When a massive star collapses into a black hole, it creates a region where the laws of physics break down. This is known as a singularity. A singularity is a point where density becomes infinite, and the curvature of space-time becomes infinite as well. Anything that passes the event horizon, the point beyond which no escape is possible, is drawn inexorably towards this singularity. Despite extensive study, the true nature of singularities remains one of the most mysterious aspects of modern physics. In the cold depths of space, dark matter interacts with gravity, but not with light. While we cannot observe dark matter directly, we know it exists because of the way its gravitational pull affects the movement of galaxies and clusters of galaxies. Dark matter is thought to make up about 27% of the universe's mass, yet it remains completely invisible to our telescopes. This invisible matter is crucial to understanding the formation and structure of galaxies. Without it, galaxies would not have the necessary gravitational pull to hold them together. Astronomers have long looked toward the stars in search of other worlds. In recent decades, the discovery of exoplanets, planets orbiting stars outside our solar system, has revealed an astonishing variety of planets. Some exoplanets resemble Earth, with rocky surfaces and potential atmospheres capable of supporting life. Others are gas giants like Jupiter, with massive storm systems and swirling atmospheres. The search for exoplanets has reignited the hope that we may one day find other habitable worlds, perhaps even signs of alien life. Space is not a perfect vacuum. Instead, it's filled with particles, radiation, and cosmic dust. Cosmic rays, high-energy particles originating from the Sun and distant galaxies, travel at near-light speeds through space, occasionally colliding with particles in Earth's atmosphere. These collisions can create dazzling displays of light, such as the aurora borealis. While cosmic rays are constantly bombarding our planet, they don't pose a threat to life due to Earth's protective atmosphere. However, their study helps us understand the high-energy processes occurring in deep space, offering clues about the most energetic phenomena in the universe. A truly mysterious region of space is the zone around black holes known as the event horizon. It is the boundary beyond which not even light can escape, and anything that crosses it is lost to the black hole's singularity. The event horizon marks the point of no return, but the strange thing is that from the perspective of an observer far from the black hole, time appears to slow down as an object approaches this boundary. This distortion is a consequence of the immense gravitational pull of black holes, which warps space-time around them. Galaxies are often thought of as isolated systems, but in reality, they interact and merge with one another, creating some of the most spectacular events in the universe. When two galaxies collide, their stars often pass by each other without direct collision due to the vast distances between them. However, the gas and dust within the galaxies interact violently, triggering massive star formation. These galactic mergers play a vital role in the growth of supermassive black holes, as the black holes at the centers of galaxies may eventually collide, releasing a tremendous burst of energy detectable as gravitational waves. As the universe ages, the stars that once filled the cosmos begin to fade away, and with them, the light they emit. Stars have a life cycle that ranges from millions to billions of years, and the death of a star can be as dramatic as its birth. When a star exhausts its fuel, it undergoes a process known as stellar death. Lower mass stars become white dwarfs, while more massive stars end their lives in explosive supernovae. These events scatter elements like carbon, oxygen, and iron into space, enriching the surrounding interstellar medium and allowing for the creation of new stars, planets, and potentially even life. The concept of time in the universe is anything but simple. Time is not an absolute, unchanging constant. It is relative and can be influenced by gravity and speed. This idea, known as time dilation, is one of the key predictions of Einstein's theory of relativity. The stronger the gravitational field around an object, the more slowly time passes for that object. This effect is most noticeable near black holes, where time almost comes to a standstill at the event horizon. This fascinating property of time has been confirmed through numerous experiments and observations. There's a remarkable place in space where time itself seems to stretch: black holes. The immense gravitational pull of these objects is so strong that not even light can escape. At the heart of each black hole lies a point called the singularity, where the laws of physics break down. While nothing can escape once it crosses the event horizon, the extreme gravity distorts space and time in strange ways. Close to the event horizon, time slows down dramatically. To an outside observer, an object falling into a black hole appears to freeze in time, stretched out by the immense gravitational forces. In the distant past, the universe was a much smaller, hotter and denser place. This state of extreme conditions marked the birth of everything we know today. Just after the Big Bang, the universe was filled with a searing hot plasma of particles, unable to form atoms. As the universe cooled, atoms began to form, allowing light to travel freely for the first time. This moment, known as recombination, left behind the cosmic microwave background radiation, a faint glow that still fills the universe today and serves as a snapshot of the infant cosmos. The cosmos may seem vast and empty, but there are hidden forces at play that hold it all together. One of these forces is gravity, a fundamental interaction that shapes the very structure of the universe. Gravity governs the motion of everything, from the smallest particles to the largest galaxies. It's the force that keeps planets in orbit around stars, and stars themselves bound within galaxies. Despite its profound effects, gravity is still not fully understood. It's only in the presence of extremely massive objects, like black holes or neutron stars, that gravity's true power is felt, bending space-time itself. What happens when two massive galaxies collide? The answer lies in a spectacular process that can take billions of years to unfold. When galaxies merge, their gas and dust collide and interact, often triggering massive star formation. The cores of the galaxies, where supermassive black holes reside, may also collide and merge, releasing an immense amount of energy. While the stars within the galaxies rarely collide due to the vast distances between them, the entire galaxy undergoes a profound transformation, reshaping the galactic structure. These mergers play a significant role in galaxy evolution. We often think of the universe as a steady, unchanging entity, but it's in constant motion. Stars are born, live, and die, each process taking millions to billions of years. Some stars die in spectacular supernovae, while others slowly fade into white dwarfs or neutron stars. These stellar deaths play a crucial role in enriching the universe with heavy elements. When a star explodes as a supernova, it scatters elements like carbon, oxygen, and iron into the interstellar medium. These elements form the building blocks for new stars, planets, and even life itself. In the cold, dark spaces between stars, there exists a strange and invisible substance, dark matter. While it doesn't emit light or energy, scientists can detect dark matter by observing its gravitational effects on visible matter. Dark matter accounts for around 27% of the universe's mass-energy content and plays a crucial role in shaping the formation and behavior of galaxies. It acts as the unseen scaffolding around which galaxies and clusters of galaxies form. Without dark matter, galaxies would not have enough gravitational pull to hold themselves together. The night sky is filled with billions of stars, but these stars are not evenly distributed. Instead, they form vast structures known as galaxy clusters, where galaxies are bound together by gravity. These clusters can contain anywhere from a few dozen to thousands of galaxies, with dark matter acting as the glue that holds them together. Galaxy clusters are the largest gravitationally bound structures in the universe. Studying them helps scientists understand how matter is distributed on the grandest scales and provides insight into the mysterious nature of dark matter. Did you know that space itself is expanding? The universe has been stretching ever since the Big Bang, and this expansion is continuing today. What's more fascinating is that the rate of expansion is actually accelerating. This means that galaxies are moving farther apart at an ever-increasing rate. This mysterious acceleration is driven by dark energy, a force that makes up roughly 68% of the universe's energy content. The discovery of this accelerated expansion revolutionized our understanding of the cosmos and led to the realization that we may not yet fully grasp the forces at play in the universe. Most stars in the universe will eventually die. However, the manner in which they die depends on their mass. Lower mass stars, like our Sun, will eventually shed their outer layers, creating a stunning planetary nebula. What remains is a dense core known as a white dwarf. Over billions of years, this white dwarf will cool and fade, leaving behind a faint remnant of the once vibrant star. In contrast, higher mass stars explode as supernovae, a catastrophic event that can result in the formation of a black hole or neutron star, scattering heavy elements throughout space. Across the expanse of space, galaxies drift through the cosmos, sometimes colliding, sometimes passing by each other. These encounters have a profound effect on the structure and evolution of galaxies. When galaxies collide, their gravitational interactions can trigger bursts of star formation as gas clouds collide and compress. The mergers also lead to the growth of supermassive black holes at the centers of galaxies. In some cases, galactic collisions can even result in the complete transformation of a galaxy's shape, turning it from a spiral into an elliptical galaxy. These mergers are essential for the evolution of galaxies. The vast majority of the universe's matter is hidden from our view. This unseen mass is known as dark matter, and it makes up about 27% of the universe's total mass. Although we cannot directly observe dark matter, we know it exists due to its gravitational effects on galaxies and galaxy clusters. Dark matter is believed to act as the scaffolding around which galaxies and clusters of galaxies form. Without it, galaxies would not have enough mass to hold together against the centrifugal forces caused by their rotation. In the infinite stretches of space, there exists an invisible web that holds galaxies together, the cosmic web. This structure is made up of vast threads of dark matter and gas, connecting clusters of galaxies across millions of light years. The cosmic web is not only an incredibly intricate structure, but it also plays a pivotal role in how galaxies are distributed throughout the universe. It helps guide the formation of galaxies and provides a framework that shapes the large-scale structure of the cosmos, influencing the motion of galaxies and how they interact with one another. At the heart of a star lies an incredibly powerful force, nuclear fusion. This process, which occurs in the core of stars like our Sun, turns hydrogen into helium, releasing vast amounts of energy. This energy is what powers the star and gives it its light and heat. Over time, stars exhaust their hydrogen fuel and begin fusing heavier elements like carbon and oxygen. When a star runs out of fuel, it can no longer support itself against gravity, leading to its death. The way a star dies, whether as a white dwarf, neutron star, or black hole, depends on its mass and composition. One of the most intriguing mysteries of the universe is how it all began. The Big Bang Theory suggests that about 13.8 billion years ago, the universe began from an incredibly hot, dense state and expanded rapidly. In the first few minutes, the universe cooled enough for atomic nuclei to form. Then, as it continued to expand, atoms began to form, eventually leading to the creation of stars and galaxies. This initial explosion set the stage for the universe's evolution, and the evidence of it can still be seen today in the cosmic microwave background radiation, a faint glow left over from the Big Bang. Space is a place of extremes, with temperatures that can vary dramatically. In the vacuum of space, away from the warmth of stars, the temperature can drop to nearly absolute zero. However, near massive objects like stars and black holes, temperatures can soar to millions of degrees. The extreme temperatures in space are a result of the lack of atmosphere, which means there is no air to retain or distribute heat. These temperature extremes have profound effects on the materials and objects in space, influencing everything from the formation of stars to the behavior of distant planets. The search for life beyond Earth has become one of humanity's greatest quests. Scientists have discovered over 5,000 exoplanets, planets orbiting other stars, and many of these worlds exist within their star's habitable zone. This zone, often called the Goldilocks zone, is the region where conditions are just right for liquid water to exist, a key ingredient for life as we know it. While we have yet to find definitive signs of life on these exoplanets, the discovery of potentially habitable worlds has reignited hope that we might one day find life beyond our own planet. As our journey through the vastness of the universe comes to an end, allow yourself to sink even deeper into relaxation. Let the endless stretches of space, the birth of galaxies, and the infinite mysteries of the cosmos wrap around you like a comforting embrace. Feel your body soften, your breath flow naturally, and your mind drift peacefully as you imagine the stars and distant worlds fading gently into the background. Rest here, in this serene space where time and space feel boundless and eternal. If this journey through the cosmos brought you peace, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated. Be sure to turn on the notification bell so you never miss another tranquil adventure. But for now, let your body relax, release all remaining tension, and allow your mind to float freely among the stars. Good night and sleep well.